In this video, we're going to expand upon the definitions of to oxidize and to reduce. So in the previous video where we looked at how to add half reactions together in order to get the combined redox reaction, we found that all of the electrons that are either lost or gained cancel out when we add an oxidation and reduction reaction together, and therefore electrons are not shown in the overall reaction. The problem with this is if we can't see whether an element is losing electrons or gaining electrons, how can we identify whether an atom is reduced or whether it's oxidized? Well, in order to do that, we can use something that we call oxidation numbers as a way to identify whether an element has gained electrons or lost electrons. So oxidation numbers simply represent the charge that an atom would have within a specific compound. In other words, whether the element gains electrons within a compound or loses electrons within a compound. Now, if this definition sounds similar to formal charge, that's because it is very similar, but as we'll see, it's not exactly the same because formal charge is used for calculating atomic stability based on whether it has gained or lost electrons, but with oxidation numbers, we're not looking for the element's stability, we're simply wondering whether it has gained or lost electrons at all, but in either case, in the same way that formal charge is determined by an element's electronegativity, we can see that electronegativity is even more important in the calculation of formal charge. For example, we know that the alkali metals like sodium have the lowest electronegativity within their respective periods, and because they only have one valence electron, we know that they're always going to lose one electron. Now, if they lose one electron, that gives them a charge of +1, and that means that this charge is also their oxidation number. Likewise, alkaline earth metals, have the same conundrum as alkali metals in that they have the second lowest electronegativity in their respective periods, but instead of having one valence electron, they have two, which means if they lose their two valence electrons, they would have a charge and therefore an oxidation number of +2. Now, hydrogen is not an alkali metal, but it exists basically within the same group because it has the same two characteristics: a low electronegativity, especially compared to other nonmetals, and a single valence electron, which means it is almost always going to lose one electron and therefore have an oxidation number of +1, just like the alkali metals. Although with hydrogen, this can go either way in certain circumstances. Now, if we go to the nonmetals, we of course need to consider fluorine because it has the highest electronegativity by far on the periodic table, and since it only needs to gain one electron to have a full valence shell, when it does gain its one electron, it has a charge of -1, and therefore we can say that fluorine's oxidation number is also pretty much always going to be -1. Likewise, with oxygen, which has the second highest electronegativity behind fluorine, its oxidation number is almost always going to be -2 because oxygen needs to gain 2 electrons to have a full valence shell. Now, what we do with these oxidation numbers is we can use these in order to identify the oxidation numbers of any remaining element that is not a metal where we know it's going to lose electrons, or a nonmetal with a high electronegativity, because just like with formal charge, the sum of the oxidation numbers of every element in a compound must be equal to the total charge of the molecule, and this again is almost exactly the same as formal charge. So if we take a look at the compounds below, we see a family of compounds that are all based on chlorine, and then a family below where the compounds are all based on carbon. So if we start with perchloric acid here. We know that chlorine has a lower electronegativity than oxygen, so we can't use the same generalization as fluorine because oxygen is going to be taking chlorine's electrons in terms of how the electrons are distributed. So if we refer to hydrogen, we know that hydrogen has an oxidation number of +1, and oxygen has an oxidation number of -2. We have 4 oxygens here, meaning that the total oxidation number of all oxygens is going to be -2 times 4, which is -8. Now, we know that perchloric acid doesn't have charge, so its total charge is 0, which means the oxidation number of chlorine must be equal to a number that adds to +1 and -8 in order to give us 0, which means that its oxidation number would be +7. Now we can see that depending on the number of oxygens and hydrogens within the compound, this actually changes. So again, hydrogen has an oxidation number of +1, oxygen's oxidation number is -2. -2 times 3 means the total oxidation number of all oxygens in chloric acid would be -6. We know chloric acid doesn't have any charge, so its total charge is 0. So we need a number that adds to +1 and -6 in order to give 0. So that means that chlorine's oxidation number here is +5, and we can see that the number of oxygens affects what the oxidation number of the middle element is going to have. If we do another example, let's skip this one. You can try chlorous acid on your own. Let's go to hypochlorous acid. Again, hydrogen's oxidation number is +1, oxygen's is -2, and again, we only have 1 chlorine here, and the total charge of hypochlorous acid is 0, so we need a number that adds to +1 and -2 in order to give 0, which means that the oxidation number of chlorine here is +1. Now, if we take one of these chlorine oxide compounds here, let's take dichlorine trioxide for argument's sake. Oxygen has an oxidation number of -2. -2 times 3 is -6. That means that the total oxidation number of both chlorines is going to be +6, but because there are 2 chlorines, +6 divided by 2 is +3. So as we can see, even if oxidation numbers initially are a foreign concept, the pattern for calculating them is relatively straightforward. With one exception, what happens when we are dealing with a compound with a total charge that is not 0? Well, if we take a look at these carbon compounds, we can try them out. So let's look at carbon dioxide to start as our baseline. So we know that oxygen has a total charge or oxidation number of -2. -2 times 2 is -4. So carbon's oxidation number to balance out the charge to 0 would be +4. Nothing new there. But what about in carbonate? Well, same thing. Oxygen has an oxidation number of -2. -2 times 3 is -6. However, this is an ion, which means the total charge that we need for carbonate is -2, which means that carbon has to have an oxidation number that adds to -6 in order to give -2, which would be +4 again. So again, the calculation of the oxidation number is not any different. It's just that the total charge is not 0 anymore. So if we take a look at the polyatomic ion oxalate here, same thing. Our total oxidation number needs to equal -2. Oxygen's oxidation number, as always, is -2. -2 times 4 is -8, which means that the total oxidation number of the carbons has to be +6, because +6 minus 8 is -2. Since there are 2 carbons, +6 divided by 2 is +3. So we can see that carbon has a variable oxidation number in the same way that the chlorine compounds above do. In the next video, we're going to add some additional terminology to our electrochemistry vocabulary, as well as look at the roots of why oxidation and reduction reactions are given those specific names.